Welcome back to another Organic Chemistry Reaction App Devlog. This one's going to be another one of a lazy one, but I'm going to talk about today Puzzle 486, which you can play yourself right now if you'd like. Puzzle 486 is a relatively straightforward puzzle from a chemistry knowledge perspective. You have two cyclopentadienes, and they react in a Diels-Alder reaction to dimerize. This is a very common reaction that gets taught, and Diels-Alder reactions aren't too complicated. It's a single step. The problem with this puzzle from a game development perspective, puzzle development, I don't know what to call it, is how many solutions there are that are unique, right? And so a Diels-Alder reaction is a reaction between a dienophile and a diene. So, of course, a diene is where you have an alkene, a single bond, and then an alkene. So this is a diene, and this is a diene. And so the diene can react with a dienophile, which is often an alkene itself. So this could be a dienophile. This double bond could be a dienophile. Whoops, I've already made an answer there. Didn't intend to do that. This could be a dienophile. This could be a dienophile. And so right off the bat, we've got two dienes and four dienophiles. And so if this is a diene, which it is, and it's going to act as the diene, then it could react as a diene with this dienophile or with this dienophile. So that's two different possible answers. And if this is the diene, then it could react with this as the dienophile or this as the dienophile. So it's another two different answers, four different answers. The other problem is that a Diels-Alder cycloaddition, you could draw the reaction arrows moving counterclockwise, or you could draw them moving clockwise, right? So in this situation, since I've already kind of started it, let's say, so this is now the diene because that's how the puzzle is. Let's call this one the dienophile. And so I've chosen to react it going counterclockwise right now. And so that gives us the answer. But let's do that again with 486. Instead of doing that counterclockwise like I just did, it's also a valid mechanism to say I'm going to do it clockwise instead, right? And it's the same answer. It makes the same molecule, but it is a different type of an answer, right? If I say I'm going clockwise, then this double bond would have to go to the center of the diene. Whereas if I'm going counterclockwise, then this one goes to the center of the diene. And so this is a valid answer. It's the one that I accidentally put in initially. And this is a valid answer. But they're not both valid together. And so I have to program separate solutions for the puzzle. So if I do this, suddenly this is now wrong, right? Which is true. You can't have both of those be right answers. They're both part of solutions, but they're both parts of different solutions. And so they can't be done together. So initially I said there were four possible answers, just based on using this as a diene and these as dienophiles. So that could be one reacting here, one reacting here, two, or this one reacting here, three, this one reacting here, four. All different answers which require different start-end values to be input, different solutions to be programmed, I guess. But then within those four, there's also the clockwise version and the counterclockwise version. So there are a total of 8 different possible solutions to this puzzle. And because they're both cyclopentadienes, there's not really any difference between them, right? You could argue that if one of them was like a furan ring instead, then it would be more likely to react as the diene or more likely to react as the dienophile. I don't actually know which one it is. And then you could argue that it will only react one way. But in this case, it's all the same. And so all 8 answers are not only equally valid, they're chemically speaking, they are the same answer. And so this is a one-step puzzle that is very easy to solve from a player's perspective, assuming they know what a Diels-Alder reaction is. But from a programming perspective, it takes 8 times longer to program this than it would like an SN2 reaction, because an SN2 reaction only has one answer and only one valid path to that answer. Nucleophile hits the electrophile, leaving group leaves. Right? That's the only answer. Whereas there's 8 different ways to do this. Dienophile 1, or with diene 1 with dienophile A, dienophile B, or dienophile 2 with dienophile A, dienophile B, and counterclockwise, clockwise for both of them. So this is a very simple puzzle, but puzzle design-wise, it's a very complicated puzzle. So that's the first thing I wanted to share with you. The second thing I wanted to share with you is the next struggle that I have in terms of puzzle drawing. So I'm starting to include electrophilic aromatic substitution reactions, and one of which involves the use of iron tribromide as a catalyst. So that's not a problem itself, but this reacts with bromine, at least according to the mechanism in one of the textbooks that I'm getting inspiration from. This reacts with bromine to create iron tetrabromide. I shouldn't have deleted that, just this, right? So that's FeBr4. And this is an anion, so there's a negative charge here. I can draw iron tetrabromide, that's no problem. The problem is this negative charge. The question is, where do you draw the negative charge? Because you could draw iron tetrabromide like this, and it's got the negative charge. The bromines will be, here, 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 here. You could just draw the negative charge here. That's an easy solution. I could do that right now. The problem with that is that it's not true to the chemistry. Iron is not more electronegative than bromine. So the electron density is not on the iron. It's actually on the bromine. So drawing the negative charge on the iron suggests that the iron itself has a lot of electron density on it. It doesn't. The electron density is on the bromines. And so you could instead draw the iron as a +3. And then you would have the bromines on the outside, and they would have negative charges. Br minus. Oof. My drawing is getting worse. Right? And so you could draw it this way instead. Have formal charges on every atom in this molecule with minus, 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 +3 for a total of -1. This is probably a better representation in the sense that it's more true to the chemistry, but just having a negative charge on the iron is a lot easier to do. My problem is that I am pushing this as a sort of authentic presentation, and so I want these puzzles to be drawn the way that a chemist would draw them. The truth is that I don't think a chemist would draw them either way. Putting the negative charge on the iron is tempting, but it's wrong, as I said. Drawing it like this is, I think, also kind of incorrect, because it kind of assumes that the bromines themselves are not even covalently bound to or there's no covalent character to the bond that the iron has with the bromines, right? So like a sodium bromide is completely ionic, and so you can draw the Br as minus, and there is no bond between the sodium and the bromine. It's just an electrostatic interaction. Whereas I think with iron, it's different. The bromine is not truly a negative charge. It just has a partial negative charge. And the iron has like a partial +3 charge. I think that's the best way of saying that. And so a different way of drawing this is basically to say, this structure has charge issues. We know that the overall charge is -1. And so instead of trying to draw it anywhere on the molecule, we're just going to put the whole molecule in some square brackets, and we're going to draw the negative charge on the outside of the brackets to demonstrate that there's a negative charge in this overall molecule. It's kind of dispersed over all of the bromines. It's not on any single one bromine, right? And it's definitely not on the iron, I'll tell you that much. So this, I think, is the way that a real chemist would draw the iron tetrabromide anion if they were forced to. The lazy ones, and I think everybody would end up being lazy in this, is to just say FeBr4 and just put a minus here, not draw any of the bonds explicitly, and then just kind of treat this as, I don't know, some sort of a weird base and not explicitly show how it reacts. I can't do that for my purposes because I really want to have all of these bonds drawn explicitly to really show what's going on, really show how the chemistry is working. So I can't just cheap out like this and just say, FeBr4 is like a single entity. It's 5 separate entities, or actually 9 separate entities for the purpose of the game. 5 atoms, 4 bromines, 1 iron, and then 4 bonds. 5 plus 4, 9. So I have to draw it explicitly, and I think the best BR the best way to do this, and the most authentic way to do this, is to have these square brackets. The real problem is that I don't have this programmed into the game. So I came up with a plan. The plan is here. Basically, I need to create a new property for a molecular charge. And I need to have 4 different of these properties, one for each molecule that's being drawn. Up to 4 is the max that I have in the game right now. I could add more, but I don't think you'll need more. And if we do, then we're in some serious trouble from like a theoretical standpoint, since most mechanisms can only involve 2 molecules, and I usually just have the other 2 as like byproducts just to show that the byproducts are there. But if you need 5 byproducts, then we have issues. So 4 properties: molecule 1 charge, molecule 2 charge, 3 charge, 4 charge. Then we'll just say if charge is 0, set the charge to 0 initially. If the charge is not 0, then we'll spawn a left bracket, spawn a right bracket, position them properly around the molecule, and then spawn a positive charge or a negative charge. And then, if you need, you can add a 2 or a 3 or a 4, whatever, as required. I think I've programmed in up to +3. +4 is pretty rare, but it would be easy for me to add a +4 if needed, or a -4. Does -4 even exist? +4 exists. -4, kind of sketchy. Yeah, and then that would be how this gets put into the game. How am I going to assign charges? So like if there is a charge, that's how it's going to happen. But how does the game know that there is a charge? What I'm going to do is within the molecule smile strings, I talked about this in an earlier devlog, maybe devlog 3 or 4. I'm going to create like a new entity that can be deduced. I'm just going to put it as a square bracket, m minus, and then close the square bracket. And then if the next atom, so I have an example here of like if this is like a pentane anion, which doesn't really exist, and the negative charge is distributed across all carbons, which again, it isn't, because this molecule doesn't exist, then, if there's an M and the next atom that you're drawing is the square brackets M minus, then instead of drawing an atom like you normally would, instead set the molecule charge to -1 or +1 or whatever. If I put a plus in here or in -2, then I can set the charge as required. I think M is an appropriate letter to use. M can just represent molecule. People use the term M plus to demonstrate like a molecular ion for mass spec, or M minus if you're doing like negative mode mass spectroscopy. They will commonly use M plus or M plus 1 if it's an M plus, or MH plus, maybe? MH plus, yeah, if it's protonated and positively charged. But where M means molecule. There is a problem where M can also be used as a symbol for a generic metal. I don't know if I will ever need that, but it might be a good idea to plan for a future where I do, because I do have like generic groups, R groups, for example. I think I have a cyclohexyl group as well, CY. And so it's might be good for me to reserve the symbol M for a generic metal and instead use a different thing. Maybe just do it explicitly, you know, instead of saying it's just M. I can't use MO, that's molybdenum, but I could just be like mol minus 1 for molecule. And that way I still have M. I don't think MOL is used for anything. Should be fine. But that's the plan. That's how I'm going to tackle this. It's going to take a long time because, again, I'm a chemist. I'm not a programmer. A programmer could probably whip this out in a day. It's going to take me a while to sort through all of the nonsense. My spaghetti code is not the easiest to work with, and I'm not the best at working with it. So, yeah, it'll take some time, but it's sort of the next step in the process. It might take a little while to get some more puzzles added because I'm going to be working on this feature. But we'll power through, and we'll get there. Sorry for the lazy devlog, but it's better than nothing, right? Thanks for watching again, and see you next time.